Um, so today it will be purely just me talking. Basically is about what is quantum after we go through all the quantum mechanics and so on, and why we want quantum computing. This is something not covered in the textbook, but I think it's good to cover. The first thing when we talk about what is quantum, when we have the idea of uh, quantum theory. I think all of you should know at this point the EPR paradox, whereby Einstein want to consider whether or not quantum theory is physical or not. So, in his paper, he tried to consider when the idea of physical means that you can describe the physical properties of an object independent of observations. So over here, you actually have two assumptions. Independent of observation means realism, and then the other one is locality, which means that whatever measurements that is done in another places, it cannot affect uh, the other parts of the measurement results. So that is what essentially EPR paradox try to say. So by showing an entangled states, and then for some reason when you measure on one party, the other measurement outcome can be predicted. So Einstein considered that, sorry, not just Einstein, but EPR basically concluded that quantum theory is not complete. Um, and then there's also another thing before quantum theory is fully developed. When you have this kind of classical intuition, basically what you think is that, let's say the physical properties of an object, whether or not you do the measurement on it, uh, the idea of the physical properties exists. So the action of measurement only tries to reveal what kind of physical properties that is. So um, this is also another thing that is kind of counterintuitive compared to the classical theory, because we know that for quantum theory, if you don't perform the measurements, that kind of physical properties does not really exist, and you cannot really fix a certain number to related to that kind of measurement, just like that. So, in other words, for quantum theory, the kind of measurement that you try to do on your physical system, it sort of like relates to what kind of measurement outcome that you get. So so really over here I mentioned like a few things. So the first thing is the EPR paradox. The second one is what we call as the contextuality. Contextuality basically means that your measurement is coupled with your physical properties. So without knowing what kind of measurements that you try to perform for quantum system, you can't really tell what kind of physical properties that you want to review. So then you can try to propose some hidden variable theory whereby it is non-contextual. So what do I mean by that? Basically, it means that there is this one hidden variable that is you cannot review it, you cannot measure it, but because of this hidden variable, it sort of like accounts to the probability aspect of quantum theory, and then you can also simultaneously assign some values to whatever observables that you have. Did I? No. Okay. So you can also simultaneously assign some values to all the quantum observables that you have determinis- deterministically, depending on the hidden variable which you cannot review. So then you can sort of think that, okay, because of this hidden variable, you can assign these values before the measurement and independent of whatever measurement outcomes that um, you can you need to measure. So of course there will be some constraints on how you can assign the values, and I think this is important. It needs to be compatible observables. So these constraints are assumed. So then Cohen-Specker sort of show that this kind of hidden variable theory does not really exist, which is trying to say that you cannot have this kind of non-contextual hidden variable theory. It is impossible to assign definite values to an observable independent of other compatible observables. So in this case, the compatible observables is what we call as the context. So the simplest proof is they use what we call as the Mermin-Perez square, which uses two cubic states. So assume that you have two cubic states, and on your two cubic states, basically what you can measure is the Pauli matrices. So these are all the possible Pauli measurements that you can perform on two cubic states. So the idea is that you try to arrange your measurements in such a way that each of these lines represents a context. And really, when you think about this, so all this would be the eigenvalue square. So it means that it can either take +1 or -1. And then under each of these contexts, they are mutually commuting, which means that they are compatible to each other. So over here, the straight lines will be um okay. I think did I mention something wrong over here? Yep. This should not be vertical. So let me go through it first. So each of these lines is what we call as a context because they are mutually commuting to each other, as you can see. And then I think there is this one line over here, which is giving you the product of -1. But the rest, when you try to find the eigenvalues, it actually gives you +1. So over here, when you see the plus, plus, and plus, plus, plus here, it means that the eigenvalues that you get from each of these contexts, when you multiply them together, it gives you +1. But only the last one, which is the horizontal, is not vertical. The horizontal one gives you -1. So if you were to, so okay, the plus, plus, and the minus over here is the quantum results that you get because you can basically try to find the expected value of each context and you would get the same conclusion over here. So you naturally get all the sign over here. So the sign here represents the quantum results. So now you can try to ask yourself, can you fix the values from each square in such a way that they will satisfy these kind of conditions? You'll find that you cannot do that because of this one line of minus. So if you were to fix, let's say -1 over here, so this has to be +1. But if you put +1 over here, then this line becomes -1, which contradicts with what we get from the quantum results. And because there's no way for you to assign definite values for this Mermin-Perez square, so it sort of proves that there is no way for you to have kind of like non-contextual hidden variable theory. So then from this particular proof, so Cohen-Specker sort of said that quantum theory has to be contextual because this is the assumption that they started with, and in the end they sort of find that you cannot do that. So that's why contextuality is a quantum. Um, you can say that it is a quantum phenomena. So another thing is, as I said before, the EPR paradox, whereby EPR sort of like say that if your physical theory is complete, then you always have some elements corresponding to that kind of elements of reality. So you should be able to predict what kind of results that you get with your complete physical theory without disturbing the system. But we also know that for quantum mechanics, if you have two non-commuting operators, then basically when you know one property, the other one will be disturbed. So then from the EPR paradox, they sort of say that either your quantum theory is not complete, or you basically cannot have a simultaneous reality when you have non-commuting operators. So the other way to sort of like try to overcome this paradox by Bells is to assume a local hidden variable model. So just now the assumption is contextuality. So now is about locality. So the idea of locality means that, like I said, when you try to measure one part, the effects should not be felt by the other parts. So so this is local. What locality means. The second part is again the same thing. You have some kind of hidden variable which you cannot reveal in reality that sort of like explain the probabilistic aspect of quantum theory. So then, what Bell's theorem try to say is that your correlations between all these different outcomes have to obey some constraint, which is called Bell inequality. There are a lot of ways for you to derive the Bell inequality. The easiest way is to use the CHSH inequality, which is as follow. So you try to assume that Alice and Bob sort of like stand in a different location, and then you prepare a pair of particles, one to Alice and then another one to Bob. So now Alice and Bob, you are free to choose two possible measurements. So for Alice, it will be A0 and A1. For Bob, it will be B0 and B1. And each of these measurements, they always produce either +1 or -1 eigenvalues. So it's the same thing as before. So we also try to say that these measurements sort of like reveal a certain physical property that this particle already possess, right? So then you can sort of like assign certain values +1 or -1 into the measurement results, which is written by the small a0, small a1, small p0, and small p1. So the point here for this particular thought experiment is that you try to consider this kind of combinations of properties equation 130. So you have a0 b0 plus a0 b1, a1 b0. The last one is minus. The reason why the last one is minus is because then you can group them into these two parts. And then you can try to test out all the possibilities for +1 and -1. So assume that you have assume that you have um, A0 and A1 will to be the same. So so you just try to consider all the different possibilities. Either A0 and A1 is the same, so either +1 or both of them are +1 or -1, or one is +1, the other is -1. So then, if let's say both of them are the same, regardless whether they are +1 or -1, then this term will disappear. And then here you will get 2 plus or minus 2. And then B naught is just either +1 or -1, right? And then now you consider A naught and A naught equals to minus A1. Then this disappear and this is +or -2. And then this is +or -1. So regardless of what kind of circumstances that you have, you find that one of these term on the right hand side will disappear, and then the other term will either give you +2 or -2. So now you try to repeat this particular experiment a lot of times, and then you will find that when you're averaging out this kind of product, of course you take the modulus, the average will always be smaller or equals to 2. So this operates under the assumption that whatever measurement outcome Alice has cannot affect the measurement outcome of Bob. And then you can fix certain values into A0, A1, B0, B1, right? So now enters sort of like quantum states. So we find that quantum entanglement actually violates this kind of formulations. This formulation, as I said, is called the CHSH inequality. So what you can do is to consider a Bell state. Then you try to assign 4 different measurements for A0, A1, and B0, B1. So A0 will be sigma Z, A1 will be sigma X, B0 will be this combination, B1 will be this combination. So then you can try to find the expectation value, which is just using basically the bra psi and then A0 tensor with B0 and then the cat psi. So you try to find all these expectation values. You find that the first 3 will get you 1 over square root 2. The last one will get you minus 1 over square root 2. So if you plug in all the values inside, so because of this minus, it gives you plus, right? So you have 4 times 1 over square root 2. So that will give you 2 over square root 2, which is strictly larger than 2. So that means that your entangled Bell state maximally violates your CHSH inequality. And because your assumption comes from a classical point of view, which means that your entanglement actually cannot be produced by classical correlations. And that's the whole story for the Bell inequality. I think this is my last slide. I just want to briefly introduce quantum resource theory. So the next thing when we try to study algorithms, basically there are three questions that we want to understand. The first one is what kind of resources are needed to give a certain computational task, and what kind of computational tasks are possible, and what will be the limitations for that particular algorithms. So the limitation sometimes can be given by your computational complexity, and what kind of computational tasks are possible. Basically, you can try to study through the Turing machines. What kind of resources are required to perform a given computational task. So when we try to do quantum computing, we always say that entanglement is some form of resource for quantum computing. So one way for us to really think about this is by quantum resource theory, which I don't want to go deeply into it. But essentially, the quantum resource theory tries to tell you what kind of quantum information processes that you can perform under a certain restricted set of physical operations. So this restricted set of physical operations sometimes can be due to like it is easy for you to perform a certain physical operations, but it is very difficult for you to perform some other physical operations. So you can think of it as entropy. When you try to reduce the entropy, it is harder than you just let the entropy increase. So there are 2 types of operations over here. The first type is what we call as the permissible operations, and these are the what we call as the free operations because it's easy for us to perform. Because this kind of free operations, they are only a small part of all the physical processes that you can perform. So then whatever operations or whatever quantum state that you can generated through this kind of free operations, these are what we call as the free states. So the opposed one, which is called the prohibited operations. So these operations are difficult to perform, and these operations are what we call as they will create the resource states. So then you can think of quantum computing as in when you try to perform non-local operations, which are expensive to perform, they will create entanglement, and entanglement is considered as a resource in this sense. Then what will be the free operations? The free operations will be what we call as the local quantum operation and classical communication. Generally, this is called LOCC. So what will be the one example of LOCC when you think about it? It is just your quantum teleportation. So you try to recall what happens in quantum teleportation. You can perform local operations like the local unitaries inside Alice and Bob. So remember in quantum teleportation, basically you try to perform some um, we almost end actually. But do I have? I should have the slide over here. Yeah. So if you look at quantum teleportation again, you begin with some entangled states between Alice and Bob. So then Alice sort of like stay in one point and then Bob go to another place. And then what is being done over here is that Alice performs some operation between the qubits that Alice has. And then after this kind of operation, Alice perform measurement, and then the measurement outcome is sent to Bob classically. So you are free to perform unitary operations on the Alice part, and then the classical communication is between Alice and Bob. So that is what is meant by local operations and classical communication. Um, you can basically perform whatever quantum operations that you want locally, and then you send over uh, whatever information that you want to send across different parties through classical communication. So one thing over here is that you cannot generate entanglement with LOCC. So the best you can do is to maintain the amount of entanglement you have between two parties, but you cannot generate entanglement. If you want to generate entanglement, you have to perform non-local operations, and non-local operations are expensive. So, which is why under this paradigm, entanglement is considered as a resource. So, I hope this sort of like adds some perspective later on when we go through all the quantum algorithms. You can try to see what kind of quantum phenomena is actually being used to sort of like generate quantum advantage. Um, Also, by the way, there are three types of operations over here. The first one is called local unitary. The second one is called LOCC. The third one is called stochastic local quantum operation and classical communication. Local unitary means you can only perform unitary operations locally. So if you perform local unitary operations, you maintain your amount of entanglement, and that is not useful because uh, you don't do anything with local unitary, which is why you need classical communication in order for you to use the entanglement. So when you think about quantum teleportation as well, after you perform the teleportation, the entanglement between Alice and Bob disappeared because the entanglement already goes to the two qubits that Alice has, A and C. And then the qubit that is originally entangled with Alice and Bob, the A and B, they sort of like disappeared. So in that sense, you use the entanglement, you use a Bell state to teleport 1 qubit of information from at least 2 port. So you need LOCC to actually perform useful computing tasks, quantum computing tasks. For SLOCC, what you require is that you have some probability of success for a certain quantum computational task. So LOCC is 100% you can do it. SLOCC is sort of like probabilistic in that sense. Um, yeah. So as I said, this is a quite a short presentation for today. I will just stop the recording.